right. Is it time to start? In the sound booth, is it good? Okay. All right, so I'm going to get my 45 minutes. How many of you are students? I think the students are gone, right? Just a couple? There was a bunch of them. I added an extra slide just for the students too. So, all right. This is the latest I've ever presented in my life. This is kind of different for me. So thank you for being here. I would say this is the presentation that I love to give the most. And it's just one part of when I teach people about performance and specifically about the buffer cache. And we're going to drill into really one very central point to the buffer cache and some of the internals. So if you're interested in Oracle internals and how the algorithms and some of the memory structures work together, then you ought to really enjoy this talk. It's a lot of fun. And I do a lot of role playing, so you don't have to remember the words so much. It's just how things kind of work. If you remember the story, then you've had a really, really good session. So we're going to talk about buffer cache throughput, and again, like most of my talks, because I'm a database server guy, it really doesn't make any difference whether it's in the cloud, on-premise, or not. It's the Oracle database server, it's the kernel, all right? So here's the situation. If you've run an AWR report, you've probably looked like this poor guy before, all right? He looks at the AWR report and he sees DB CPU, that's foreground process CPU, and then he sees free buffer weights. He's like, what is free buffer weights? What does it mean? What am I supposed to do about it? What are my solutions? How do what do I do? Okay. Really, I'm going to talk about many different things today, but the focus is going to be on free buffer weights. So that's really what the presentation is about. But along the way, we're going to talk about DB file sequential read, the free buffer weights, read by other session, write complete weights, LRU, latch weights. So there's going to be a number of different weights that we're going to talk about. That's why I really enjoy this presentation. So, all right, so my name's Craig, longtime Oracle DBA, and this is the kind of thing that I do right here, all right? So I would love to hear from you guys too. If you're interested in the membership program, check that out. Okay, there's nobody. I don't have anybody in Paraguay yet. That would be fantastic. So, all right, that's my email, Craig@orapub.com. I would love to hear from you. Okay, so here's the topics. We're going to start talking about the key buffer cache memory structures, because there are many memory structures, but really for us, there's just a couple of them that we really need to know about. And the one that we're going to focus on is the least recently used lists, or the LRUs. That's how we typically talk about those. And then as I explain how the algorithm works, it will just naturally happen, like the free buffer weights will just kind of appear in the conversation. And it's kind of interesting how it just like, oh yeah, that's a free buffer weight, right? And if I do my job well, I really won't have to detail the solutions to free buffer weights, because you will know that by understanding the algorithm and the story behind how this happens. So that's how I tell how good of a job I actually do. And then, but I will talk about solutions very quickly, because with 45 minutes, I'm out of time, and then I'll give you just some pointers on some things if you want to even learn more. Okay? So that's what we're going to talk about. It should be a lot of fun, actually. All right, the structures. This is my battery must be starting to go dead here. All right, so this is kind of background information. We need to make sure this is clear. So, all right, so over here. Okay, yeah, perfect. Let's say this is the buffer cache right here. Okay, so this is like a spreadsheet, right? All right, that's the buffer cache, and in the buffer cache are blocks that have been brought into the cache, right? All right. Now it's important for us to understand especially in this session, that a buffer is considered free if the contents of the buffer matches what's on disk. There's no difference. And I don't even mean like a row transaction kind of way of thinking. We're talking like bits and bytes. And that's important because if what's in memory matches what's on disk, that buffer can be replaced and there will be no corruption. So that's why. Okay? So a free buffer does not mean it's empty, right? That just means what's on memory matches what's on disk. Okay? We good with that? All right? Okay. So if it's dirty, it just means there's a difference. So there could be like a byte change here, and now it's different than what's on disk. It's dirty. It's not that it's been bad. You're a dirty buffer, no. It's not that there's corruption, there's a problem, or there's something wrong. There's just a difference. Okay? All right, now this is super important to understand. The database writer writes the dirty buffers to disk. Okay? And, okay, see, if you're following me, if the buffer is dirty and the database writer writes, which is basically a copy of that dirty buffer to disk, now what's in memory matches what's on disk, and so the buffer is not dirty, it is free. Thank you. All right, good. I'm glad you're close so I can hear it. Yeah, that's what happens. So the database writer makes dirty buffers free. Okay? All right? So that's going to be important to understand. Okay, we can also have a free or a dirty buffer that is pinned. Okay? Pinned. Oh, I'm glad I have the water here because let's say this is the buffer right here. Okay, so here's the buffer, one of them. And this, as you can see, it's got some rows inside of the buffer right here. Okay? And if I have it pinned, it's like I have my hand on it. And what this means is I will not allow anybody to pour out the water and to, let's say, put some Coca-Cola in here. Okay? Can't do that because I have it pinned. So you cannot replace the contents of this buffer because I have it pinned. Now, multiple Oracle sessions can pin the same buffer. And as long as there is one session pinning the buffer, it's like off limits to being replaced. So that's very important. It's very similar to when a cursor in the library cache is pinned, you can't deallocate the cursor memory. It's the same kind of thing. It's like a kind of a protection mechanism at the buffer level. Okay? So that's really important to understand that. And that will be reinforced as I go through the algorithms a little bit later. Okay, so as I said before, there are many lists in the buffer cache, but the ones as performance-minded DBAs, the ones that we care about are the cache or the hash buffer chains, the LRUs, and the write list. Now, the write lists are sometimes called the dirty lists. That's what I mentioned before. When I learned about Oracle, they were always called the dirty lists. So that's how I naturally think. Okay, and I will repeat this multiple times throughout the presentation, but the cache or the hash buffer chains, they are used to answer the question, is a block already in the buffer cache? See, that's an important question because if it's already in the cache, there is no need for me to do a physical I/O, get that block, and put it in the cache. So that's a very important question, and it gets asked frequently. How about that? A lot, all right? So that's what that structure is used for, but that's not the focus of today. Maybe if I get invited again, I will get to talk about that because that's an entirely different presentation. The LRU chains. Okay, the LRU chains are used for this. Let's say I go to the cache buffer chain structure and I ask, and I say, hey, is the block I need, is it already in the cache? And the answer is no, it's not. So now I'm thinking, oh man, now I got to go do the physical I/O and I get the block, but where am I going to put it? Right? I can't just like close my eyes and spin around and say, okay, let's put it here. You can't do that. It's not going to work. You're going to corrupt the database. So I use the LRUs to tell me which buffer I can replace without causing a problem. Okay? And so, also, the LRUs are used to keep the popular buffers in the cache. And that's why one reason why we have a cache is so we don't have to do physical I/O because the popular buffers are already in the cache. So the LRUs are kind of a dual purpose list. Okay? All right, the right list is where some of the dirty buffers go to. And I always say, when I talk, right, remember this is the buffer cache. The cache buffer chains are over here. The I/O subsystem is down here in the front. And the LRU that I'll be referring to will be across the stage here. Okay? And then we'll have some write lists, which are typically very short, and those will just kind of be right here. And so the write list is where the dirty buffers go that the database writers kind of feed off of and write to disk to make those dirty buffers free. Okay? Now, I want to go over this part really quick, all right, because it's kind of really cool, really interesting, but it's not so important for our discussion. But I think it's pretty neat. So these lists, okay, listen closely, because this is, if you haven't heard this, it's like, what? You know? These lists are not made up of the buffers. They're not. There's another structure, yet another structure, and there's these little chunks of memory that are called buffer headers. And if you've ever looked at $, but especially $BH for a buffer header, you'll notice there's a lot of pointers, like previous and next pointers. That's because it's the buffer headers. They are what is on all these lists. And one of the pointers of the buffer header will point to its associated buffer. So in the shared pool, which is like what? Yeah, in the shared pool, this is where the buffer headers reside. So each buffer header will point to an actual buffer. See, the buffers contain the data, right? Like user data. The buffer headers contain information like about the buffer. Like where is it on one of the LRUs? Where is it in the cache buffer chain structure? See, it doesn't contain data, right? Like rows, you know, that kind of thing. All right, now when we learn about these structures, there we go. When we learn about these, it's very, very straightforward actually, okay? And at the top here, this is the cache buffer chains. These are some cache buffer chains. Now usually these things are very short. The length is 0 to maybe 1 or 2. And we want them to be extremely short because we use them to answer that question, is a block in the buffer cache, right? So we need the answer to be very quick, okay? And I'll say a little bit more about that. Now this is important to understand, okay? Every buffer in the buffer cache, we need a way to find out if it's already in the cache, right? As I said before. This means that every single buffer in the buffer cache must be represented on one of the cache buffer chains. If it's not on a cache buffer chain, we can't find it. It's like having a telephone number and it's not in the telephone book, and everybody goes to get telephone numbers by going to the telephone book. Right? So it has to be there. So that means if I have thousands and thousands of buffers in my buffer cache, and the length of these cache buffer chains are 0, 1, or 2, I'm going to have thousands and thousands and thousands of these little cache buffer chains. Okay, so if you picture that, it's very short structures like this. Okay, in fact, I think I have a page coming up about that. Now, the LRUs are very different, though. These are not used to answer the question, is a block in the buffer cache? They're used to find a buffer that I can replace, right, with a block from disk so I can get it into the buffer cache. So there's not that many of these. There's maybe 48, 64, maybe 100 or so. There's not very many. So if you have thousands and thousands of buffers in your buffer cache, the LRUs are going to be really long. They could be hundreds or maybe even 1,000 buffer headers long. whereas the cache buffer chains are super short because they're used to find things. Okay? That makes sense? We good? All right. Good, good. All right. And the write list can be, they're super short. They're like a few blocks, few buffers, because the database writer writes those to disk. Okay? We don't want those to get very long. That means the database writers are falling behind writing the dirty buffers. Okay? All right. Now, oh yeah, the really cool thing, before I show you the really cool picture, is, most people think of it like these simple linear structures. But if you think about it, like right here, I know it's really hard to see this in the back, but that's BH for buffer header number 6. Okay? Buffer header number 6 is right here. It's also here on one of the LRUs. So it's like we have this buffer header, okay? It's on one of the cache buffer chains, but it's also on one of the LRUs, which means it really is much more interesting than that. It's more like a three-dimensional kind of thing. Now that's cool, right? And that's not so cool, but it's more useful to understand, and that's my favorite right there. Okay. I have a tool on my website you can download, and you can create these things. It's so cool, and that you can rotate them in 3D and zoom in, and it's, have fun. I don't know how useful it is, but it's actually a lot of fun. All right. Okay, so that's kind of a little bit of background about what these structures are about before we get into the algorithms. Am I doing okay? You guys with me? I'm not talking too fast, right? Translators are good? Oh, I got it. Okay, good. All right, good. I like it when I can see them, because then I know how fast I'm going. Yeah. All right. So, okay, let's put this in perspective, all right? Because part of solving Oracle performance problems is understanding in kind of the life of a transaction or the life of a SQL statement where the friction is, where the stoppage is. So in order to be able to do that, we need to understand kind of the story that's involved in these processes. So let's start with a user process or a client process, such as SQL Plus or Toad, SQL Developer, or an application server process. And it has a connection that's related to a foreground process. Okay? Then the foreground process is able to read Oracle blocks from disk and put them in the buffer cache, and it is able to read and manipulate data in the SGA right here. And it has permission to do that. Or of course, the user process can't do that, because I can write a user process, right? And Oracle does not want me to directly manipulate the data in the shared pool. I could try, but that'd probably cause some problems. So the user process, SQL Plus, says, okay, I have this SQL statement, I have this text that needs to be run. So I'm going to take the text, I'm going to send it to the foreground process with an instruction to, first of all, parse it. And then, if I'm successful, execute, and then if it's a select statement, I will then fetch, right? Come on, parse, execute, and then a fetch. Okay? So I send the SQL statement to the foreground process, and it parses it. And this is all I'm going to say about parsing. It's kind of a horrible thing to say, but this is all I'm going to say about parsing. When parsing is complete, the SQL statement is ready to execute, and the information is in the library cache in the data dictionary. That's all I'm going to say about parsing. Okay? All right, now it's time to actually execute the statement. All right, this is what we are going to focus more on this. So I'm executing a SQL statement, and the data dictionary and the execution plan, through that I discover as a foreground process, because I'm a foreground process now, that I need to access a particular block. So my question is, well, where's the block? So I go to the cache buffer chain structure, and I say, hey, is the block I need already in the buffer cache, right? And it says yes. I'm like, oh, that's great. What's the address? So I get the address, I go over, and there it is, and I can access it. But that's too easy, and we would be done with the presentation too. So the answer is not going to be yes. It's going to be no. Okay? Is the block in the buffer cache? No. Oh, shoot. All right. Now I have to go get the block, and I got to put it in the buffer cache, but where do I put it? That's when I access the LRUs, because the LRUs tell me which buffer I can replace. All right? Okay. So that's kind of where this fits into the story. And when we talk about the LRUs, it's going to be more detailed. Okay, this is the slide I threw in. So how many are students? Did some students come in later? No? No, okay. I'm so bummed out. These guys were so fun to talk to. All right, well, because when I was in school, I learned about hashing, right, and B-star trees and all that, but I had no idea, like, how does anybody ever actually use this kind of stuff, right? Well, when I talk about the cache buffer chains and it's a hashing structure, well, this is one of the things you learn in school right here, right? I'm looking for a particular block. I take that file number, block number, I convert it into a hash value, like in a SQL statement, we get a hash value from text, and then I take that and I create, it's an address, but you can say like, it was gonna tell me where to look in the structure for that block. Gonna create it into a hash value, and then it's gonna basically tell me where to look for it. Okay, and you say, I'm gonna hash, you actually say the words, right? I'm going to hash to a bucket. And so if this block is anywhere in this entire structure, it must be on the chain right here, in this case, on bucket number 5. Right? Now we can see that it's not there, there's nothing there, right? But of course a foreground process can't. It can't see like a 3-dimensional perspective. So it has to go to this bucket 5, it has to get permission to scan the memory structure, which means it must acquire the associated latch. Once it does that, then it can start scanning. And it's going to say, hey, are you my buffer? Wait, there's nothing there. That means the block is not in the buffer cache. Okay, now I need to go to the LRUs to figure out where I can, or what block I can replace. Because I'm going to have to get the block from disk and put it in the cache. All right. How are we doing on time here? We're barely doing okay. Okay, I'm going to talk through, you can download all these slides from my website, because I'm going to skip through some of them because there's a lot of text and you won't remember that, and it's no fun reading text to you guys anyways. You know, it's not like a bedtime story, right? It's like, oh, Craig, thanks, read to me about Oracle. No, it's not like that. All right, so if you ever want to know how many LRUs you have, that's how you tell right here. Okay, and so there's not that many. In this system, there's not that many, okay? Remember, every Oracle memory structure, before we can access it, we must acquire what's called a latch, okay? Or a mutex if it's in the library cache, okay? But think of a latch like a token. Let's say this token is associated with a particular, linked list. Okay, well, I will have to acquire this, and I will repeatedly ask for it until I get it. And if I spin like too many times, I will back off and sleep. I will wait back up, consume more CPU trying to acquire it again until I get it. Once I get it, then I can start accessing the memory structure. But I can't do that until I get the latch. That's kind of the gatekeeper. That gives me permission to access that. And if you're not familiar, if you're very new to Oracle, right, that we need to do that because we have to make sure multiple sessions are not actually like modifying, right, the same memory structure at the same time. See, Oracle, the whole multi-user kind of thing, it's a complete illusion, really, right? Because at the bottom, at the real core guts of the product, the memory structures, you can't have somebody changing it while somebody's looking, or have two people change the same thing, right? But it looks like it happens on the outside, but we know better because like we're the Oracle people, right? All right, so that's how you find some of that out. Now let's get to the fun stuff. This is the best part of the whole presentation here. All right, so Oracle has changed the algorithm over the years, and every new release, I run this little script that I'm going to show you a little bit later. And Oracle used what they call the standard LRU, and I'm not going to get into that. Then they modified it, so they call it a modified LRU. And then they modified it again, and that's what the documentation says. But what we typically call that is the touch count algorithm. Okay? And the reason it's called a touch count algorithm is because in $BH, there's a column called TCH for touch count. And that value loosely represents the popularity or the value of a buffer, individual buffer in the buffer cache. The higher the touch count, the more popular the buffer is. Kind of makes sense. Okay, that's the good news. Okay, the bad news is if it's popular, it gets reset to 0 every once in a while. Okay? So that means you can't just take a snapshot of the buffers and say, okay, the buffer with the highest touch count is the most popular. No, because what if the most popular just had its touch count reset to 0? Okay, so that's something to keep in mind if you think, oh, I'm going to write some really cool SQL scripts to find the most popular. But no, it's not so simple. You have to sample repeatedly to do that. All right. Okay, so some things that we got to talk about. Okay, each LRU, and there's multiples, okay, will kind of look like this, or we virtualize it like this, okay? It's made up of buffer headers, and remember, each buffer header points to a buffer on disk. Each buffer header points to the block, right, that it's associated with, and the buffer headers tell me, the previous and the next pointers, okay? So it's full of pointers. That's kind of what it is, okay? All right, each LRU has what's called the LRU end of the LRU. Yeah, if you're new to Oracle, if I repeat it, it's going to sound just as ridiculous as it sounded the first time. Okay. This is the MRU end, or the most recently used end of the LRU. And generally, right, the more popular buffers will stay over here, and the non-popular buffers will kind of be over here. But that's not, you can't look at it precisely like that anymore, and you'll see why here in just a minute. Okay, so in this touch count algorithm, by default, there's a 50-50 split right here. So like right in the middle, or like I'm blinded right now, this will be the midpoint. So the buffers over here are called the cold buffers. Rocket science, right? Because this is the cold region. And then these are going to be the hot buffers in the hot region, okay? All right, so let's go. I'm going to talk through the next 6 pages or something like that. So this is where I have to watch my time. I'm getting short, I can tell. I only have 15 minutes. All right, you guys ready? This is the fun part. Okay. You ready? Okay, good. All right, so I'm a foreground process. So if I had the right T-shirt on, I'd have a big F in G for foreground right here, okay? But I don't have that, so you have to imagine this. Oh, you also have to imagine there's a big LRU right here. Can you see the buffer headers? You got to be able to picture this in your mind. Otherwise, you'll go to sleep, okay? So you have to kind of get into this. Okay? All right, so we got the buffer headers right here, okay? This is the LRU end of the LRU, okay? As a foreground process, I'm executing a SQL statement. The data dictionary and the execution plan give me information, so I know I need to access a particular block. Where's the block? I go to the cache buffer change structure, and I say, hey, is the block I need in the buffer cache? And the answer is no. Otherwise, it's so simple. It's like it's already in the cache, and we'd be done, right? But we want to have some more fun, so the answer is no, it's not in the buffer cache. And then I say, shoot, now I got to go do a physical I/O, but when I get the block, where am I going to put it? I have to go to my LRU. So I go to the LRU, but before I can start scanning it, looking for a buffer to replace, I have to acquire something. What do I have to acquire to access the memory structure? Latch, exactly. So I will go through that spinning and all that stuff that I talked about, which is an entirely very cool presentation, but we don't have time for that. All right, so I have the latch. So I have the latch in my hand right here, okay? Got it in the pocket. And now I go to the first buffer header right here. Can you see him? He's right here, okay? All right, I say, hey, are you a non-popular free buffer? Okay, now think about that. He's got to be free, because if he's not, I can't replace him. That means he'd be dirty, right? And I'd corrupt the database. So I don't want to do that. That's not part of my programming, is to corrupt the database, right? It's not good. So and if he's popular, I certainly don't want to replace a popular buffer. That's one of the purposes of the cache, is to keep the popular buffers, right? So I ask him, I say, hey, are you a non-popular free buffer? And he says, hey, man, I'm pinned. Back off. I'm like, oh, okay. He's pinned. I can't mess with him. I go to the next one. Okay? Now I'm burning CPU, right? As a foreground process, I can only do two things, right? Burn CPU or waiting to burn CPU. Because as a foreground process, I live to burn CPU. That's like how I breathe. If I have to wait, I'm just like, this is ridiculous, man. Why am I even existing right now? So I don't like that. So I go to the next one and I say, hey, are you a non-popular free buffer? And he says, I'm dirty and I'm popular. I'm like, oh, okay. That's good to know, right? So what do? All right. I remove him from the LRU and I promote him, the words promote, to the MRU into the list, and I hook him in the list, okay? Now, this guy thinks he's really popular right now, right? But it's not a problem because part of my job, I don't know, I don't want to make the sound funny, but what I do to his touch count, I go like this. I reduce it to 0. So this guy was popular. Now he's literally a 0. He's nobody, okay? And so he's feeling pretty bad right now, but I don't care because I've got work to do, right? I'm still burning CPU. I go to the next buffer header. I say, hey, are you a non-popular free buffer? He says, man, I'm free and I'm popular. I'm like, dang. Okay. I remove him because I want him to be in the cache. I remove him from the LRU and I promote him because he's popular. Okay? I put him at the MRU end of the list. What do I do to the touch count? Right, why not? Right? 0. He's a nobody. Literally a 0 at this time. So I took care of him. All right, I go to the next one. Now, as a foreground process, I'm starting to get kind of frustrated. Okay? Because I'm looking for that buffer to replace, and I'm not finding it. I'm burning CPU. My user out there is saying, Craig, what are you doing? And all he knows is CPU. Well, that's what the DBA hopefully knows, right? The user's just like, the system's slow today, right? Well, what do you mean slow? Oh, I don't know. It's just slow, man. You know, so that's real helpful, right? And so I have my job to do. So I'm really getting frustrated. I go to the next buffer header, and I say, hey, are you a non-popular buffer? And he says, I'm pinned. I'm like, okay, that's it. It's not happening, man. It's not working. So I go to the database writer, right? And I kick him because there's probably dirty buffers on here. Now, I don't have all day to do this, right? So there would have been more dirty buffers that I would have promoted, and I forgot this, or moved the non-popular ones to the dirty list. So it's very, very likely that the database writer is not able to remove the dirty buffers fast enough for the rate which foreground processes need free buffers. So what I'm going to do when I get super frustrated, okay, and this is key to the entire presentation, okay? All right. If I get frustrated enough, I will kick the database writer to wake him up, because remember, he sleeps every once in a while for 3 seconds. So he could be asleep right now, and I don't like that. And then I'm going to stop, and I'm going to yell out, free buffer wait. That's the free buffer wait, right? I'm frustrated. I can't find a free buffer. I kick the database writer, and now I go to sleep. I literally just stop. Feels kind of nice right now. Stop. Right? The documentation says 10 milliseconds, but if you actually look at the wait times, they're all over the place. So there's something else going on here that I know nothing about, okay? So I wake up. Okay. Now, this is important also. Remember, when the database writer writes dirty buffers to disk, what's on disk matches what's in memory, so those buffers become free. And the database writer knows where to reattach those free buffers on the LRUs. He puts them like right here, right at the LRU in the list. So when I get up from my sleep, I'm like, oh man, that was good 10 milliseconds, power nap. And now I go to this free buffer over here, and I say, hey, are you a non-popular free buffer? He says, man, how'd you know? I said, well, I just figured the database writer's doing what he's supposed to do. And he is, and so I pin him, okay? All right. Now, I'm not quite ready to do that yet, though, because I forgot a couple things, all right? All right. I forgot the non-popular dirty buffer, right? Are you a non-popular free buffer? He says, I'm dirty, and I'm not popular. Okay, clearly, he does not belong in the buffer cache. He's not popular, and he's dirty, so he's useless to me. So I remove him from the LRU, and I put him to the write list, which the database writer will eventually make him free. Okay. Now, I've skipped a bunch of stuff here, but I want to mention this because this is it's easy to get this mixed up. When the database writer writes, it's not like an ice cream, ice cream scooper. I don't know how to translate this, but you scoop ice cream out, right? You literally remove ice cream and then you put it in your dish to eat it, right? So the database writer does not do that. The database writer does not scoop out rows and throw them to disk. It copies what's in memory, what changed, to disk. It makes it free. The rows are still there, right? If it scooped out the data, then it would be empty and it would be completely worthless to everybody. So there's no scooping, right? It's a copy. That's important to understand that. Okay. I think that's that part. Okay, we're doing okay. You guys with me so far? Everybody good? All right. Think you're going to remember this? Yes. What's this? That means yes, right? Okay. So let's do it a different way. Now I take off my foreground process shirt and I put on my buffer header shirt, right? So I'm a buffer header here, and because what happened, remember when I said I pinned that buffer header? So I pinned them. So it's gotcha. Okay, now I am able to pour out the water and put in Coca-Cola, which is a new block. Okay, so what I'm going to do is I'm going to take that, I'm the buffer header, so I've been whoa, I've been pinned, and I'm moving, I'm being moved by the foreground process, and he puts me in the middle right here. So I'm boom, I'm on the LRU. Okay, that's where I start, and as a buffer header, I point to a buffer right here. Okay, but the content is going to be replaced, right, by a read from the I/O subsystem. Okay, now being in the buffer cache is pretty cool. Okay, as a buffer header, that's where I want to be, right? And if I was going to open up a club, right, I would call it the cache, right? And if I was really bold, I'd call it the buffer cache. But I'm not going to do that because I have work to do right now. So I'm standing here, I'm pinned right here, and now what's going to happen is the foreground process is going to do that physical I/O. Okay, so the foreground process, now I'm a foreground process. Sorry, I'm switching back and forth. Sorry about that. I have my FG shirt on again. Okay, I have that buffer header pinned. Okay, I know where to put the buffer or the block from disk. Now it's time to do the I/O. Okay, so I'm still burning CPU, and I say, what time is it? I write that down, and I do the physical I/O, and I wait till I get it. DB file sequential read, DB file sequential read, DB file sequential read. Here's the block. Get it? What time is it? That's the wait time for that single block read. Now I'm burning CPU again. I've got the block. I know exactly where to put it because the buffer header points to it. It's in the cache. And now I can access it, and so can you. Pretty cool. Okay? It gets even better than that because let's say that you needed to access that same exact buffer. Okay? The same buffer that I'm going to access for whatever reason. Now, you could do a duplicate I/O and say, well, I'm going to read it myself. Who cares what Craig's doing? But you're smarter than that, right? Somehow you figure out that I am doing this I/O for this block. And so you're going to say, you know what? I'm not a fool. I'm not going to do a duplicate I/O. I'm going to wait for the read by the other session to complete. And once the block's in the cache, then I'm just going to access it. So the wait of it you will post will be read by other session. And it is one of the few wait events that actually tells us what's going on. Because you literally are waiting for the read, right, by the other session, me, to complete. And once I complete it, I can access it, and so can you. So that's how the read by other session wait event comes into play of all this. It's pretty cool how it actually kind of all works together. All right, so now I'm a buffer header, okay, and I'm in here, and it's pretty cool. I'm pretty happy about myself right now, and I have a touch count of a 1, right? I'm oh, this is cool, right? But what do I see in front of me? A foreground process. the big FG, right? And I'm like, uh-oh, he's going to ask me, am I a non-popular free buffer? I want to be popular because I want to be in the cache because that's the place to be, right? So I'm walking here. Oh, and as other buffers get moved into the cache, right, that's going to naturally move me down the LRU. As other buffers get promoted, that will push me down to the end here. So it's like no fault of my own. I will naturally just start to kind of migrate to the LRU end, or the LRU end of the LRU. Okay. Uh-oh, that's my timer. All right. So as I'm migrating here, I get touched because I'm a popular guy, right? So it's like ding, ding, ding. And then the foreground process, hey, Craig, are you a non-popular free buffer? And I said, I'm popular. And really, you and I both know free or dirty doesn't make any difference at this point. It's all about the touch count, man. All about the touch count. So I get promoted. I'm feeling pretty good about myself. And I do the buffer swagger. Sorry, I get carried away here. So I do the swagger, and I'm feeling pretty good about myself. And then what happens to my touch count? Right? Down to 0. I'm feeling really good about myself, right? All of a sudden, I'm a total 0. Right? My life sucks. It's horrible. I'm a buffer header. Nobody likes me. I'm a 0. But as I live in the cache, I slowly start to migrate down here. Hopefully I get touched. But it really doesn't make any difference yet because when I cross the midpoint, touch count gets reset to 1. So now is when it really counts. So now I'm hoping like somebody touch me. Somebody, boom, ting, ting, ting. I got touched. What's your touch count? It's 5. Okay, whew, made it. And so now I get promoted again. I'm feeling really good about myself. What happens? Oh, touch count down to 0. I'm a stinky nobody, you know. And you go through this like emotional roller coaster, right? Forever, as long as I'm popular, I get promoted, touch count down to 0, I get touched, promoted. As long as I keep getting touched, I can stay in the cache. Okay? So that's kind of the life of the buffer header right there. I don't know, I guess it's a good life. I don't know, whatever. I get too carried away. All right, so that's kind of how it works. Do you guys believe me? I wouldn't believe that either, okay? So what I did is I wrote a cool little script here, and I'm going to go over this really, really fast. And the answer to what I'm going to show you here is on the next page. So don't take a picture of it, okay? And you can download this. This is a timeline right here. What I did is I put a load on a system, and I found a buffer that was kind of busy, or kind of active, kind of not. So it flipped back and forth, okay? So every half of a second, I checked $VH, or BH, for its touch count. And the touch count is the vertical axis right here, right? Here's the 0 line. Where's my, it's in my pocket. It's the latch, right? Here's the 0 line right here. So if it's less than 0, that means the buffer or the block is not in the cache. It's been replaced, okay? If it's 0 or greater, it's in the cache. All right, so now remember the whole story here, like the demonstration and how this relates to what you're going to see here, because this is actual Oracle running right here, not just me making this up, okay? So we start with this buffer header, this buffer, touch count is 5 right here at the top, okay? All right, so it's kind of like I'm right here, my touch count's 5, I'm feeling pretty good about myself, right? Yeah, I'm popular, I get promoted, what happens? Touch count goes to 0. I'm like, oh, that sucks, right? And then what do you know? I crossed the threshold, touch count 1. Uh-oh, somebody touched me. I get replaced because I'm not popular. I get replaced. But then just a little bit later, boom, somebody said, hey, Craig, I need you back in the cache, man. I'm like, oh, cool. So I get brought back in the cache at the midpoint, touch count 1. And then life is good because it's like, ting, ting, and I'm popular. So what happens? I get promoted. Touch count goes to 0. I'm feeling pretty good. Well, I'm not now, but I'm hoping I'm going to get touched. Sure enough, I cross the threshold, touch count 1, ping, ping, ping. I get promoted. Touch count goes to 0. And so you can just kind of see as I go out of the cache and I come back in. So when I get a new version of Oracle, I run this little script and I plot that, and I should be able to detect if something very significant has changed. Because I don't know anybody in Oracle that's actually going to tell me this, right? And it still is there's still a lot of things that could be changed, and this would not detect that. All right. Okay, we're gonna end with this, and then I'll kind of tell you what the final slides say, and if you're really interested, you can just look at it yourself. Okay, free buffer weights. Remember how free buffer weights started, right? I went to the cache buffer chain structure and I said, hey, is the block I need in the buffer cache? And the answer was no. So there was a need for buffer replacement. See, if there was no need, I would go straight to the buffer cache. I wouldn't do any of this LRU stuff. But I had to do the LRU stuff because I had to find a non-popular free buffer. Why? Because I'm going to do a physical I/O read. And before I do the read, I better have a place to put that block. So there has to be a need for buffer replacement. Okay. So if I free buffer weight, I will try to reduce the need for buffer replacement. All right. How can you do that? Maybe a bigger buffer cache. Maybe you tune the really crappy SQL that's doing all those physical IOs, right? How about I have a faster IO subsystem? See, there's multiple ways we can attack this just on the need for buffer replacement. It's very easy to find the SQL because it is the high-consuming physical read SQL. It has to be there. It cannot hide, right? It has to be there. If there was no physical IO SQL, we would not be scanning the LRU. We could not get a free buffer weight. It has to be there. You will find it. If you can't, email me, all right? And I'll find it for you. Just click, and you'll see it. It's easy. Okay, the other one is that there's almost always DML. Now, I didn't have time to, really spend a lot of time here, but usually what happens is that there's DML, and these buffers get really dirty right here because there's so much DML. And so the foreground process is unable to find that free buffer quick enough because not only is it promoting buffers, right? Buffers are pinned, but there's a lot of dirty buffers. Okay, and so there will be some DML SQL. I've never seen free buffer weights without there being DML SQL. Okay, so find that. Okay, you'll be able to find it. Now, you can't go to users and say, stop changing so many blocks, right? It doesn't happen that way. So maybe it's a batch process. Maybe you can modify the workload. Don't know. Okay, so that's a tough one. Okay. What's usually happening also is the database writer is falling behind. There's so many dirty buffers, it literally cannot pull those out of the LRU fast enough and write them to disk to make them free. All right, so if the database writers are falling behind, what do? Right, it's not a rocket science thing here, right? You add more database writers. I mean, it's that straightforward. Unless there's an IO bottleneck, right? The same kind of thing. You don't have a bigger buffer cache if you don't have enough operating system free memory to support that. You don't add more database writers if there's already an IO bottleneck, okay? If you do that, nothing will happen other than it could get worse. So you need to understand what's happening at the operating system, okay? So, usually what happens is that if you can significantly just change one of these three, you can get rid of free buffer weights. Okay, it's like a chair with 3 legs on it, right? And if you just kick one of those legs, the free buffer weights fall over, and you beat it. You win that game, or that round. How about that? Okay, so what I just talked about is kind of detailed in here. Here's an example of how to resolve the issue. And let me go back a second. I did a little video on YouTube showing you how you can create free buffer weights, how simple it is. But understanding how something is created gives you a lot of clues about how to uncreate it, which is resolving the problems. So and I detail how to do that. It's a fun little video. At least I think it is. All right. Just so you know here, when I added more database writers, there was no decrease in free buffer weight percentage right here. 20, no change. a tiny increase in block changes per second, a tiny increase in logical IOs per second from our baseline. That's because there was an IO bottleneck. And I tried to add, and I added database writers anyways, okay? All right, that's it. More info on my blog, on my website, and I do a bunch of training on this kind of stuff. Buy my stuff. Thank you for listening. All right. Have a good rest of the conference. All right. They cut me off already. That's brutal. All right. So I think I'm the last speaker, at least in this room, and there's 2 other sessions going on right now. So I think there is like a closing session. Yep. There is. Okay. So stay put. There's something really good's going to happen. I don't know what, but all right. Okay. That's it for me. Thanks again for listening, you guys.